for the introduction. I hope you can see my screen. Indeed, I will talk about, we've already covered a lot of the fabrication aspects. I would now like to talk a little bit about design, because that is what we specialize in at PlanOpSim, to make the design of metasurfaces as easy as possible for engineers and scientists. We do this through our design software that we have brought on the market since 2021, and also through design services that we do for various companies and research institutes. And our tool scale, when you want to design a metasurface and integrate it into an application, you need to design from the nanoscale pillars over to large area components and then integrate these into a system. And these are actually the different design skills that we also incorporate into our tools. So our team can support, in fact, the whole workflow through our software and our services from the very initial step. So we've seen here refractive optics, diffractive optics. And the first question that a designer always has to ask is, well, what type of physical mechanisms, what kind of optics do I need to use to solve these problems? Metasurface is not the solution for every problem, but it does give a lot of new design options. So in this concept stage, we are already supporting our users. Then we go on to model systems. This is traditionally done in ray tracing because there are that many free variables that the only way that you can really model a system is through ray tracing. But we inform the ray tracing with the capabilities of the nanostructures that come from our full wave solver. And then we use these libraries of structures, integrate them into full components, which can go up to the centimeter scale. We validate that and we integrate that to fabrication as well. I will show a couple of examples of this in the next series of slides, but the rapid iteration through these various steps is very important if you want to take something from a nice academic curiosum to a real product, and that's why we support this as close as we can. The first step is always to design the nanostructure. So this is sub-wavelength scale, so we need full wave Maxwell solvers for this. Anyone that has done Maxwell solutions knows that it's very time consuming, but it is very accurate. And we in our software use the RCWA algorithm. Other people use FEM or FDTD. The bottleneck remains the same actually in this case, that you need to calculate these whole structures. The results are the same. We pick RCWA because it's generally faster than the other methods. The main question that you have here in the design is what should the structures look like in order to reach the performance that I want? This is typically phase and amplitude control, but could also be polarization control, for instance. We implement for this various types of algorithms to help you optimize that. So you see here a benchmark of 7 different parts. We find that particle swarm and covariance matrix, for instance, as well as Bayesian optimization, tend to work really well, both on reference problems as on actual problems. But all of these are a designer choice that has to be made while they are designing, and we allow that, of course. So here you see typical, let's say the Pancharatnam Berry type design that is seen in a lot of papers. It's not so practically useful, but it's a good reference problem. And then once we have our library of nanostructures, of course, we want to go on and make functional components like lenses out of that. Then we go on to the component design. For instance, here we have a small lens that we've generated as a demonstration. So what you do as a designer is you identify through ray tracing or through theory what's the required lens profile, the wavefront that you want, and you map that back to the different structures that you have available that can be manufactured. Then you calculate what should the shape look like, what's the GDS, what's the projected phase function, and what's the final efficiency, point spread function, and so on and so forth. So all of that is then calculated. In this example here, we're just using titanium dioxide pillars, but it's completely up to a designer, of course, which structures to use. And some of the speakers here have already covered that it's generally a good idea to have high refractive index contrast. That's why we're looking at these dielectrics for this type of design. And once you have the design, you can have it manufactured. So we produce the GDS file directly. This is an example that was created by one of our customers. So they use the software to generate this IFTA phase-only hologram meant to project an image onto the asphalt. The GDS rolls out and is fabricated. Here you see an SEM image and performs as a very compact projection optic that is then used and measured and was up to 70% efficient. That doesn't sound like a lot, but if you use a conventional projector, those are actually only 10% efficient. So this is a very nice step up from that. For practical applications, we need large sizes of design. And if you look at conventional methods of designing this, especially the full wave simulations, they are typically restricted to at most 100 microns or something of that area. By using multi-scale simulations, we are actually able to design much larger areas in a practical time frame. So we go up to 10-15 millimeter is the current design limit of our servers that we use, and this can still be done in reasonable times of almost 2 hours, but still in good time. So we can go 22,000 times larger than what you can do in full wave, and we can do this in short times so that we can iterate rapidly through different designs. We can also apply different methods to have more accurate calculations of the nanostructure's behavior. So some of you that have a bit experience with this know that often people rely on using the pillar as if it's surrounded by all the same structures, where in reality they are different structures. This is called the local periodic approximation. It's a very fast way of calculating, but it comes with known limitations, especially if we go to high numerical aperture lenses, for instance. If we use an overlapping domain analysis that also takes into account the surrounding pillars, we can still calculate rapidly because we are working on subsections of the lens and iterate through the whole lens. We can calculate large areas without having to full wave calculate them, which would blow up any high performance computers' memory limits. So we can still do this in this way. And then we can go on to fabricate these metasurfaces. So if you don't have your own fabricators, the photonics world has since a long time known the concept of PDKs, process development kits. Since 2023, manufacturers are offering established PDKs for supported wavelengths of 940 and 532 nanometer directly as a way to design. So as a designer, you actually don't need to worry about which structure specifically to use. You can select the corresponding vendor's PDKs, run the design for your target wavefront, and then go through the design and send that straight to the manufacturer. So this is another aspect of rapid prototyping, rapid iteration that is developing and a sign of growing maturity for the metasurface market. We can also establish the fabrication effects through Monte Carlo simulations of fabricating a metasurface. So if we have a nominal design and we then start to randomly introduce errors into that fabrication process, as will happen in reality, the simulation allows to estimate the effects of that. And this distribution plot that you see here, in fact, contains 25,000 different lenses that were simulated in different ensembles. This is something that's only possible, again, through the application of multi-scale simulations. So that's fine. We can make fabricatable single components. We can also then integrate that into systems through plugins to ray tracing solutions. So the color router was already mentioned earlier today. As an example, what we have shown here is that a designer can first design its lens system and then through a DLL plugin, import the specific behavior of the metasurface into the refractive ray tracer and use their elements of the metasurface design, which are precisely the ones that you couldn't reach using refractive optics, such as this multiplexed wavefront color router here. So we see the blue wavelength is focused on the blue subpixel, the red wavelength is focused on the red subpixel. We have this nice color splitting that you wouldn't see with a conventional optical lens. All of this is directly available and used by many of our users. I've talked a lot today about design, and I would like to wrap up here with stating that when we think about bringing a technology to market, we don't just need design, and a design tool is not just something that's used by a designer, but in fact, the whole ecosystem has to develop, and I think Metasurfaces is coming along very nicely here. And there is PlanOpSim's role specifically. So we can offer to the ecosystem design solutions and expertise to make sure that your products are fully integrated and well designed. And we are looking for partnership with all of you to improve the accessibility of meta and nano optics all over the world, to improve design for manufacturing, and to develop the high performance simulation tools needed to make this as fast and efficient as possible. Thank you very much.